dog. Done. Let me get these guys. All right. And let's share the screen. Start the broadcast. Cool. All right. Does somebody have a question? No? I don't know what that sound is. That's totally irking me. Okay, let's see. So as far as announcements go, one, I hope everyone enjoyed your weekend, right? So we are at the top of week 5, right? So let me see. So exam 1 was due this past, last night at midnight, right? So Sunday night at 11:59 p.m. from going into last night into this morning. But do not fret, right? With all of our assignments on Pearson, we get unlimited attempts, and you can work on any assignment past the due date with only a 10% late penalty. All right. So if you haven't submitted it for whatever reason, you can still get it submitted and still earn up to a 90%. Trying to think. Another update is that, so I've created a folder where you can access basically all the stuff that you see me writing. You can access a PDF version of it in our notes, right? So I think I loaded like a copy of the student notes in advance, where basically it's like the definitions and theorems and corollaries and stuff like that. And then it's each example, but it only has the question. It has no supporting details. So then with each session, I intend to load basically our session right at the end of class. So as soon as class ends, you get a copy of the PDF. You can access it. I went on and loaded all the back files. So what you're going to see when you open up the folder, because I'm basically dumping all of my notes from all my classes into one folder. So you'll have access. And I try to make the labels relevant, where it has the time, the week and the day and the time of what that document's about. So you can find yours and you can browse my other classes. You can even watch the presentations from the other classes, because all those are live streamed. As usual, if you have questions, feel free to unmute yourself to get my attention or type in the chat. I do check the chat periodically. And as a reminder, this is remote asynchronous, so you're not obligated to stay. As long as you've got into my Zoom, which if you can hear my voice right now, more than likely you're in my Zoom, right? That means you've gotten your attendance credit. So that's what I need from you guys on any given day. And I fill the air with just like the lecture and the notes just to fill it, the lecture and the homework. But if you guys want to talk about something else, we can. Trying to think if there's anything else. Yeah, I think that's the meat and potatoes. Exam 1 was there. So what we're going to be doing this week, we're continuing chapter 1, and we're going to be working on section 1.4. Right. So with this being Mondays, I usually like to go through as much of the lecture as I can. Whatever we don't finish together, there is a recording of all of this entire section already. You should have access to it, right? And then on Wednesday, we'll take some time to go through as many homework questions as we can. I do want to encourage you all to seek out the tutors. It's a good idea to definitely be in contact with the tutors. You can take this information and sit down with the tutors and work on it, and it's totally okay. I encourage you guys to work together. You've already paid for the tutors at Morehouse, right? These guys, they should definitely be able to help. You've already paid for their services, so just seek them out, go sit down with them. Get what you can from me. If it's not clicking with me, which, I understand, because you guys choose to, I've been there. Sometimes you just can't, it's hard to get it from the professor. You do the best you can. Then you team up with your classmates. Then you team up when you go to tutors. You keep kind of trying to get it from multiple perspectives until something clicks, right? Until it clicks. I'll check Zoom again in just about 9 minutes. For any stragglers, I usually like to check it again around 2:15, and then from there, give it a little bit of time for the latecomers to kind of get together. So let's take some time and start making our way through section 1.4, a library of functions. A few objectives here. We like to define linear functions, discuss important properties of functions, graph square root and cube functions, evaluate and graph piecewise functions, graph basic functions, and then find the average rate of change of a function. Okay. So let's decide. Can I get a volunteer to read this slide for me, please? And thank you.
Let m and b be real numbers, the function f of x equals mx plus b is called a linear function. If m equals 0, the function f of x equals b is called a constant function. If m equals 1 and b equals 0, the resulting function f of x equals x is called the identity function.
Okay. Does anybody so feel like, can you translate that text into your own words? Like, what does this mean? Can anybody like translate this for us? Okay. Let's give it a chance. Okay. So, basically what we have linear functions. So, the root for linear is line, right? So we're talking about lines. It says let m and b be real numbers. So then this function, this is basically y equals mx plus b, right? And just instead of y, they put f of x, which is the same thing. This is the linear function. So whenever we're talking about linear functions, y equals mx plus b is a great place to start or to have ready to go. If our slope is 0, then the function becomes f of x equals b, right? So this term basically goes to 0. And so then you have f of x equals b, which is a constant function. So this is going to be y equals some number. The graph is going to be just a horizontal line. If your slope is 1 and the y-intercept is 0, then we're working with what's called the identity function. It's like basically y equals x. All right, and it's called the identity function. Okay, that was good. So the graph of f of x equals mx plus b. The graph of a linear function is a non-vertical line with the slope m and y-intercept b. Right. So notice here when you trace the graph from the left to the right, the graph rises. With the second one, and the slope is positive there. With the second one, as you trace the graph from left to right, it falls. Right, and the slope is negative. So when we have a positive slope and we trace left to right, the graph rises. When we have a negative slope and we trace left to right, the graph falls. Okay, I feel like that's intuitive. Say our slope is 0, right? Then we're talking about the constant function, and f of x equals some b. We have a constant function. Basically, it's a flat horizontal line through y equals b. And then say the y-intercept is 0 and your slope is 1. This is called the identity function. This is like y equals x. Right? It's an identity function, right? So those are some of our basic functions that we're going to be manipulating in going forward, right? So here we x write a linear function given these 2 points. Now with my earlier class, I did it a way that I meant to introduce at the end of the semester, but I didn't even think about it until after I submitted it. I was like, oh, I totally did that out of context. But it's fine. It'll pop up. It's, it's okay. So here we're given g of 1 equals 4 and g of -3 equals -2. So these are 2 ordered pairs, right? So the first piece of information is saying basically when x is 1, the corresponding y is 4. The second piece of information is saying when x is -3, the corresponding y is -2, right? So then if we want a linear function, we might be working with something like y equals mx plus b, right? So we have 2 points. Maybe we might also use the slope formula, right? Let me see. Slope equals y2 minus y1 over x2 minus x1. And this is our slope function, right? So I think these 2 is enough information for us to move forward. Now, I'm a fan of whenever I have ordered pairs, I like to just label them x1, y1, x2, y2. Okay. So let's find the slope. Let's find the slope and then see one possible way to go ahead and solve for the y-intercept. So then our slope is going to be y2, which is -2, minus y1, which is 4, over x2, which is -3, minus x1, which is 1. On top, it looks like we get -6. On bottom, it looks like we get -4. This reduces down to a +3/2. Okay, so we have our slope. Okay. So then maybe we can use this and one of the pieces of information to solve for B. So what I'm going to show in this next part, actually, I used to always just default to the point slope form, but I had students in the past that showed me, well, you can actually use the y equals mx plus b. And I researched it, and to me, I felt like their technique was much more simple than what I was doing. So I like to promote what they were doing because I checked it. What they did was fine, and it was more simple. Right, this is a game of simplicity. So I'm going to plug in that slope, and I'm going to plug in 1 comma 4 into y equals mx plus b. So then my m is 3/2. My x, I'm choosing that first point, so my x is going to be 1. We're trying to solve for b. And when x is 1, y should be 4, right? So we have one equation, one unknown, so we can solve. I'm going to shrink these guys down. So I really just want that to be reference. I need some space. I can shrink it down a little bit more, actually. Let's go. Okay, let's see. What's the time? Okay, let me finish this one out. So then basically I was just making some space. So let's continue over here on the right-hand side. So then we get 3/2 plus b equals 4. So then ultimately b is going to be, let's see, 4 over 1. So then 8/2 minus 3/2 to give us 5/2. So then we found our slope and we found our y-intercept. So then let's go back and find our function. So that means our f of x, or I guess it should be g of x, just to keep our labels proper. G of x should be 3/2 x plus 5/2. Okay. Okay. Let's copy this. Copy, come on. Okay. And then now something like this, we can actually check before we go forward, right? And I'm gonna just do a quick check. We're saying that when x is 1, the corresponding y should be 4, right? So then 3/2 plus 5/2 is 8/2. 8 divided by 2 is 4. So this one checks out. Okay. The second one is saying when x is -3, y should be -2. So then this is going to be what? -9/2? -9/2 plus 5/2. -4/2, which is -2. That checks out. Right. So we checked both points in the function that we generated. So this should be good. G of x equals 3/2 x plus 5/2. So first you see they found the slope. Now they use the point slope, right? So once they found the slope, they use the point slope form, but you'll get to the same conclusion that we got to, 3/2 x plus 5/2. Okay. So let me take a moment there to kind of go check Zoom. See if we got any scragglers. Oh, we got a good amount of scragglers. Okay, let's pause this for a moment. Let's get these guys. Okay, let me see, who do we have? That's fine, thank you. Right here, we got him. Got him. Got the student. And the student. Cool beans. All right. Okay, let's go back to sharing the screen. Let's try that again. There we go. Okay, if you're just joining us, welcome. We are working on section 1.4, library of functions. Okay, let's get back to the slide. I don't know. Hopefully we didn't lose any of our work. We left off here. Okay, so we found a linear function that passed through these 2 points, and I think we got the same thing as the notes. So also, if you're just joining us, so all the stuff that you see me writing, now I'll make a copy of the PDF of everything that I'm writing available after each session. If you were to go in the box right now, if you go in the Blackboard, open up our main folder, there's going to be a folder that says box link. In that folder, you'll find these notes for not only today's session, but the past sessions as well. Since I have like 4 sections of College Algebra 1, I went on and just put all of my sections into one folder, and I tried to make the labels relevant so that you guys can find your stuff. And you can browse stuff from my other classes as well. You can also watch their sessions too, because I live stream all of my sessions with all the students. So you can go and watch those as well if you wanted to. Can I get a volunteer to read this one for me, please? On increasing, decreasing, and constant functions.
Let f be a function, and let x1 and x2 be any 2 numbers in an open interval contained in the domain of f. The symbols a and b may represent real numbers, negative infinity or positive infinity.
Then, okay, let me go through this. We'll recap one more time. Let f be a function, and let x1 and x2 be any 2 numbers in an open interval. AB contained in the domain of f, then the symbols a and b may represent real numbers, negative infinity or positive infinity. Then we have the following properties. So we say that f is an increasing function on an open interval AB if when x1 is less than x2, that implies the corresponding y1 is less than y2, right? So pictorially, what that means is basically, like if you consider this open interval, whenever you trace the graph left to right, it's gonna go up, right? This thing on the left is just like a detailed explanation of what's going on, but pictorially, all it's saying that as you trace the graph left to right, it should be increasing. It should be going up, okay? So if this is an example of increasing, then naturally we could talk about an example for decreasing. We say f is a decreasing function on the open interval AB if whenever x1 is less than x2, that implies f of x1 is larger than f of x2, right? So that pictorially, that means as you trace it left to right, the graph should be going down or falling. Okay, we talked about increasing, decreasing, and then we can also talk about constant. So we say f is a constant on an open interval AB if whenever x1 is less than x2, that implies f of x1 is equal to f of x2, right? So pictorially, what that means is as you trace the graph left to right over that interval, the graph is going to be flat or horizontal, okay? So from the graph of G, find the intervals over which G is increasing, decreasing, or constant, right? So as we kind of trace from the left to right, now when we give our results for increasing, decreasing, or constant, we're talking about as you move along the x-axis, right? So as we start from the far left on the x-axis, what is that concept called? If you go to the far left on the x-axis, how do you capture that? The far left. So far left on the x-axis is going to be negative infinity, right? So as we trace this from the left to the right, it's increasing as x goes from negative infinity up to here, right? The x value here is what? -2. So we say the graph is increasing as x goes from negative infinity to -2. And for this discussion, we use parentheses. I'm going to abbreviate it with an up arrow. That means it's increasing the function is increasing as x goes from negative infinity to negative 2. Then the next checkpoint, something happens as x goes from negative 2 to 3. Right? So between negative 2 and 3, the graph is flat. So as x goes from negative 2 to 3, it's constant. So I'm gonna capture that with a flat horizontal line. And then as x goes from 3 to the far right, which is going to be positive infinity, the function is decreasing. Okay. So as usual, if anything is not clear, you just have to like get my attention. So feel free to either unmute yourself or type in the chat. Let me check the chat really quickly. The chat looks healthy. Do we have any stragglers? Okay, cool. All right. And you can see here, it says it is increasing from negative infinity to negative 2. It's constant on this interval, and then it's decreasing here. Okay, let's keep going. Can I get a volunteer? Go ahead.
So when I was taking the actual exam yesterday, some of the images that you're like teaching about were on the quiz. However, I did not see them on the practice. So is there like any like way like why? Because I was a little bit confused about that.
So if you're just going, it's not really the images. Like you might have similar images that overlap. Like you can have images that are in section 1.3 that we're also going to talk about in 1.4, but it's less about the images and more about what concept are they talking about in regards to that image, right? Because basically all the things that we're talking about are like, it's like building, right? So we're in section 1.4, we're building on things that we talked about in 1.3. So that's why some of the images are going to look similar, but it's not about the image. It's less about the images looking similar, and it's more about what concept are they talking about, right? And so that exam was over sections 1.1, 1.2, and 1.3, right? So that's why you're going to get that overlap. But the exam, it should have been restricted to sections 1.1 and 1.2 and 1.3, right? But again, you will have some images that are in 1.3 or even 1.2 that's also going to be in 1.4. But it's not about the images; it's about the concept that they're talking about. Like what is it that they're trying to get you to pull out of the image, right? Because it could have been like domain and range. Just as a number of things that you can talk about that could have popped up. But I really like that question actually though. That was because it made me think. I like it. Thank you. Oh, give me just a moment, guys. Oh, that looks so good. I guess my friend just made a Caesar salad. I'm about to do the same when I get up with you guys. Ooh, that looks so yummy. Okay. She sent me a picture of it. I'm like, come on. All right, let me see. Yeah, let me get somebody to read this one. If you don't mind, please and thank you. Also with like that exam question, we can pull it up and, we can talk about it if you want to talk about it further. Like we can look at whatever question you're referring to. And then I can like point to you like, hey, this is where that came from in the book. If you want to do that later on. All right. So let me see. All right, that's the end of that. So let's see. Definition of relative max and relative min. If A is in the domain of a function f, we say that the value f of A is a relative minimum of f. If there is an interval x1, x2 containing A such that f of A is less than or equal to f of x for every x in the interval x1 to x2. Wait a minute. Oh, okay, relative minimum, right? Okay, here. Let's just finish reading this and I'll go back and give a recap. So we say that the value f of a is a relative max of f if there's an interval x1 to x2 containing a such that f of a is greater than or equal to f of x for every x in the interval, right? So what this is saying, if you have some x that's in the domain of a function, we say that f of x, or that f of that a, we say it's a relative min of f if there's an interval x1 to x2 that contains a such that basically that y value is less than all nearby y values for every x on this interval that we're considering, right? So the simple explanation there is that that's basically going to be the bottom. Relative min is basically the bottom of a valley, right? So it's that y value that's going to be less than all nearby, less than or equal to all nearby y values. And then similar for a relative max, right? So this is like the technical definition. I feel like this becomes more clear when you look at an example, look at a picture or two, and this becomes more clear. But the first one is basically talking about the bottom of a valley, and then the second one is talking about the peak of a mountain, right? So relative max of f, if there's an interval such that basically that y value is greater than or equal to all nearby y values for every x on that open interval, right? And here's a pictorial representation. So here's a couple of examples of relative mins, right? The bottom of valleys, and then relative max is going to be the peak of the mountains. Okay. Okay. So then the next concept that we want to touch on is what do we mean by an even function, right? So a function f is called an even function if for each x in the domain of f, negative x is also in the domain of f. And we get this, right? We're going to come back to that in just a moment. The graph of an even function is symmetric with respect to the y-axis. What does that mean to say that the graph is symmetric with respect to the y-axis? What does that mean? Or what does it mean for something to be symmetric? What does that mean?
It's on the y-axis.
Okay, what about it's how it relates to the y-axis? It does. What does it mean for something to be symmetric? Like, can you give me an example, or what does that mean?
Like parallel lines or no?
Okay, parallel lines are symmetric, right? Because you can bisect them and one side is going to match the other, right? So things that are symmetric, when you can cut them down the middle and one side is going to be the mirror image of the other, right? Examples are like, so many things. The human body or a square, TV, box, I don't know. A lot of things. You can cut them in half. One half is the mirror image of the other. You can, with this graph, you're going to be able to cut it along the y-axis, and the left-hand side is going to be the mirror image of the right-hand side. So then algebraically, when we want to test whether a function is even, right, we want to do this. So basically, we evaluate f at negative x, and then if we get back to the original, then that means that the graph is even, which means that it has y-axis symmetry. But this guy right here is the definition of a function being even. Okay, okay, that's algebraically how we're going to do it. And then if we could talk about a function being even, we can also talk about what do we mean by a function being odd. A function f is an odd function if for each x in the domain of f, negative x is also in the domain of f, and we have this, right? So when we evaluate f of negative x, we get negative of the original, right? Whereas with even, when we evaluate f of negative x, we just get back to the original. With odd, we get negative of the original. Okay, the graph of an odd function is symmetric with respect to the origin. So origin symmetry it looks like if you cut along the x-axis and put your thumb like on the origin and rotate the top half 180 degrees, it'll match the bottom half. Another way of visualizing or conceptualizing origin symmetry, whenever you have any point x comma y, you also have negative x comma negative y, right? But in either case, when we're trying to determine whether it's even or odd, we evaluate f of negative x. If we get back to the original, we say the function is even. If we get negative of the original or negative times the original, then we say the function is odd. Okay, that's the definition of even and odd. So here we actually determine whether each function is even, odd, or neither. What time is it? 2, 3, 4. Okay. I think this is right. Okay. So for part A, if we want to test for even, odd, or neither, we need to evaluate g of negative x, right? So when I do substitutions, I like to start by replacing each x with a blank set of parentheses. All right. And then we said if we're going to do a test for even, odd, or neither, we replace each x with negative x. All right. So the blank parentheses help me to keep track of my sign, so I'm less likely to make a mistake with my signs. Now, this first term, we have negative x to the power of 3, right? So this means negative x times negative x times negative x, all right? If we multiply a negative an odd number of times, will the final result be negative or will the final result be positive? If we say negative x times negative x times negative x, will the final result be negative or will it be positive? Okay, let me check something. You guys are okay. Yeah, it's always tough. Like after that lunch hour, it's so hard to talk about this. Like first thing in the morning at 9, we be all fresh, we good to go. 1 o'clock, we kind of hanging in there, but this hour, it's tough. It's like the later in the day it gets, the harder it is to do this stuff. Also, whoever does the most talking does the most learning, right? So that's the only reason I know it is because I talk about this stuff day in and day out, right? So if you're like mute, your chances of getting it are drastically reduced. So just mentioning that. If we have an odd number of negatives, it's going to be negative, right? So this first term is going to be negative x cubed, right? But the second term, again, terms are things that we add and subtract. Factors are things that we multiply and divide, right? So here's the first term minus the second term, right? So if we say -4 times negative x, double negative is positive. So then that's going to be plus 4x. So then the question is this the original? And that's going to be no, right? So let's factor out -1. If we factor out a negative, we're going to get x cubed minus 4x. Is this negative times the original? All right. Is this negative times the original? Yes, right? So this is negative g of x. So since we have g of negative x equals negative g of x, that means that this function is odd. Okay, I'm kind of out of space. I'm going to give myself some space. Man, I am feeding though. Like now, all I'm thinking about is like eating some lunch or food or whatever, and then taking a nap. And I know it's such a bad habit. So I try to counter that by I try to eat light, so that way because I know I'm gonna get sleepy. I'll be sleeping anyway. So then it's like, well, let me try to eat a little bit light, so that way if I sleep on it, then it's not gonna be so as bad as if I eat like burgers and fries and then try to lay down. Anyway. All right. So we got that one is odd. Can I paste? Let me see. Yes, that'll work. So we got that's odd. Yeah, let's copy. Okay, let's work on part B. It's a little bit better. Okay. So for part B, we're doing even, odd, or neither. So we wanna evaluate this at negative x. So we want to replace each x with negative x. So we got f. First, I'm going to replace each x with a blank set of parentheses. And then I'm going to plug in my negative x. Plug in my negative x. Okay. So then this is going to be, if we have an even number of negatives, that's going to be positive. Is this the original? I'm going to say
Yes.
Sorry about that, guys. For some reason, Zoom decided to just do an automatic update like in the middle of my presentation. I'm like, okay. But that's okay. It seems like it's okay, so I'm not going to worry about it. Let's keep moving. This is where I noticed it cut off. I don't think we had too much of a difference. So we have f of negative x equals f of x. That's the definition of a function being even. Okay. Let me do what I did before. I like here. And come on. You're not gonna, okay, that's fine. Let's copy, paste. And if anything is not clear, you just have to feel free to unmute yourself to get my attention. Let's try the last, let me check Zoom one more time. The chat looks clear. Let me get the straggler. Just a moment, so I don't forget. Ho, ho, ho. I am feeding fast, feeding fast. H-I, there he is. Cool, okay. Man, that name sounds like it's straight out of Jumanji. The next level. That's so interesting. Okay. This is so interesting. Okay. So here for part C, we want to test for even, odd, or neither. So same thing, we're replacing each x with negative x. I'm kind of out of space. Okay. Instead of jamming that in, let me kind of, I'm going to resize it. I just don't want to, I don't want to be jammed. Let's try this again. I'm just going to kind of work right here for the time being, and I'll move it around. So again, we're replacing each x with negative x, 2x cubed plus x squared. And again, we're putting a negative x, negative x, negative x. Okay. So then, again, if we have an odd number of negatives, this term, again, terms are things that we add and subtract. Factors are things that we multiply and divide. So this term should ultimately be negative. So we're going to have negative 2x cubed. In the second term, we have an even number of negatives. So that guy's going to be positive. So plus x squared. Is this the original? They're not the same. And I think even if we factor out a negative, they still don't match up. So this is an example of neither. Okay. Let me kind of do a quick scan. So odd, even, and neither. Okay, so a piecewise function, when you start working on piecewise functions, a piecewise function, all it is just it's several graphs on the same Cartesian plane, right? It's just that each graph is restricted to a certain domain, right? So you have to, when you go to graph them, you can graph them like normal, but then you got to erase the part that you don't need. Okay, just trying to be as precise and simple with my words as possible, because otherwise it gets jumbled real fast and easy. Evaluating a piecewise function. To evaluate f of a for a piecewise function f, first determine which line of the function applies to the number a, and then evaluate f of a using the line chosen from step 1, right? So here we have an example of a piecewise function. Again, if we were graphing this, we would graph this like normal and graph this like normal. Y equals x squared, y equals 2x plus 1. But this one is restricted to when x is strictly less than 1. This one is restricted to when x is greater than or equal to 1, right? Okay, so if this is restricted to x is strictly less than 1, that means we're talking about the numbers to the left of 1, So we would graph this like normal and then erase the right and keep the left. This one, x is greater than or equal to 1. So we would erase the left and keep the right. Okay. So then here, this the x is defined f of 0 and f of 2. So when x is 0, you got to ask yourself, do we use line 1 or do we use line 2? If x is 0, right, that means we're to the left of 1, so that means we will use line 1. So then 0 squared is 0. For this one, when x is 2, because 2 is to the right of 1, we're going to use line 2. So then 2 times 2 is 4, that's going to be a 5. So the first one is 0 and the second one is 5. Okay. You see the 0 here and you see the 5 here. Okay, we're just about out of time. Let me see. Okay, I don't think we did this one with my earlier group. I'm gonna just do a quick, I'm not gonna work this one, I'm gonna just give an overview of it. So to graph something like this, right, you can just graph y equals this first line like normal, and then y equals this one. But the first one only applies when x is strictly less than 1. So you would keep the left-hand side of this graph. The right-hand side, you would erase it. And then this one applies when x is greater than or equal to 1. So you would keep the right-hand side of this graph, and the left-hand side you would erase, all right? And there's a little bit more to it, but we are out of time. Did you guys want to ask any questions? Let me go ahead and load a copy of this. So I'm gonna send it to Box. That's the wrong location. Fall, College Algebra 1, into the note section, updated daily. So I went on and loaded all the notes from previous sessions, and then every time we finish a session, I'll dump the PDF there so you can pull basically anything that we worked on together. Additionally, that same PDF will have like the remaining notes. I think I went on and loaded all the student version of the notes, where the student versions have definitions, theorems, and corollaries, and it has an introduction to each example. It has the question for each example, but none of the solutions, right? So the recommendation is to attempt the student version ahead of time, see how far you can get into that. And then when we meet, I'll load the results or the answers to all those examples, right? So that's what I just loaded for this section. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.
Have a good one.
Have a good one.